Okay, on the second problem, or problem 3, I'm sorry, we have clock times and depth. If we graph depth versus clock time, the graph will look something like this. And we're going to say, it says in the problem, that this point here, this last point where x is where the clock time is 810 seconds and the depth is 30 millimeters, represents the vertex of this curve. Okay, so vertex, well, has a certain meaning, but we're just calling this point the vertex. And then we define y to be the vertical distance from the vertex to a given data point, x the horizontal distance from the vertex to the same data point. So for example, for the data point 61, 130, the vertical distance from the vertex to that data point is represented by this arrow. And we can see that the vertical distance is from vertical point 30 units above the x-axis to 130, so the vertical distance is 100. The horizontal distance is here. And that's from 61 to 810, which is 749. And of course, the vertical distance represents distance in millimeters. And this is a change in clock time actually in seconds. Okay, so this is not y versus x, and this graph is not y versus x. Y and x are defined here, so when you do a table of y versus x, for the first point, the y value is 100. Of course, y will be in millimeters, and x will be in seconds, and x will be 749. Now you can do similar calculation for every point. Okay, the relative point is the vertex, which is at 810 seconds and 30 millimeters. So relative to the 30 millimeters, the second depth is what? 30 millimeters to 110 is 80 millimeters. The next depth is 90 millimeters relative to 30 millimeters. That gives us a y value of 60. And it's very easy to calculate that the next two, or the next three, are 40, 20, and 0, including the last point, which is the vertex, so it's at 0 distance from the vertex. Okay, calculating these distances relative to the 810 second. Okay, well, we're going to subtract 136 seconds from 810, and that should give us 674, I think. And I'm not going to stand here and figure all these out in my head while you watch. I'll make my mistakes and then write them down here so you don't have to suffer through watching me do this. Now, if I've done these correctly, of course the last one is 0, 0. 380 and 430 does add up to 810. 504 and 296. 504 and 300 is 804. So I've got a mistake there. Let's fix it. That should have been 514 instead of 504. And 602 and 208 is 600, 200 is 800, 2 and 8 is 10. That gives us the 810. Okay, so I believe these are correct. Okay, now what we want to do is we want to sketch a graph of y versus x. Okay, the instruction didn't say construct a graph of depth versus clock time. It said construct a graph of y versus x. So first we got to follow the definitions of y and x to obtain a table so that we can construct a graph. I'll do that off camera. Okay, I've set up a graph scale. 0 to 100 is easy. 0 to 749, well, I went 0 to 800 because 800 is easy to subdivide. Cut it in half, you get 400. Cut that in half, you get 200. And then cut this interval in half, and you'll find your location for 600. Now let's go ahead and plot the points. Again, I'll do this off camera. Okay, these points aren't really well located. You could improve on this, but right there are the approximate points. And if I now draw my curve, of course 0, 0 is also a point. The curve is going to look something like this. Now there is our y versus x. Nobody that got this problem, I think at least a couple of you got it, did this. Nobody sufficiently read the instructions to understand, I think, that you needed to follow the definitions of y and x. You just took this and fairly naturally decided, okay, this is y versus x. That was confusing, so I didn't know what to do with it. Well, understandable, but take a lesson. You do have to read the details, okay? And they can be hard to understand. It's not trivial to understand this, but one of the things we're trying to accomplish here is to at least understand the necessity of reading very carefully and thinking about what everything means and knowing when you've got a good interpretation. Okay, so anyhow, here we've got it. Now, where does this problem go from here? Well, we're trying to determine the characteristics of this graph. So we start by thinking, well, what happens to y when x doubles? So take a look at it yourself. What do you think happens to y when x doubles? Okay, in order to answer the question of how y changes when x doubles, we start pick an x. I don't mean pick a number for x. You could. Okay, that wouldn't be totally invalid, but I want to just pick a point here. Again, my favorite point of the x-axis of the way this picture is drawn is right here. Okay, so I just picked my favorite point. If I'd have picked a point out here, then, well, if I pick this point, I can double it, and then I can double that. And then I might even be able to double that, but probably not. Had I picked a point out here, which might have been even better, I could have cut that in half, cut that in half, and cut that in half, and maybe even cut it in half again. Okay, well, anyhow, I picked my favorite point. I'm stuck with it. So here it is. Here's my favorite x, my favorite point of this line. Okay, now, that's this far. If I double it, it comes out to about here. Let's stand back and check that. Does this look like it's equal distance from here and here? I guess so. Okay, then we double that value. So I just want to pick a set of doubling values of x. So let's see, from here to here. It looks pretty good. This looks like it's about as close to this point as it is to 0. Okay, so now I want to project up here and look at my y values. Okay, so let's see. Okay, that looks like a pretty good estimate of the y value corresponding to my first x value. Now let's go to the second x value. And my y value is here. And then let's go to my third x value. Okay, I have to go up. A little hard to see what's a straight line. Let me stand back here and, okay, I think it comes up to about here. I don't mean straight line, I mean a vertical line. It's hard to see that from this angle on the board. And also there's some distortion due to the camera. Anyhow, it puts you about here. So right here are 3 y values. Now the question is, by what factor does the y value change? Well, let's see, let's just take this one. 1, 2, 3. Looks like it's pretty close to 4. Looks like maybe a little less. This one is 2, maybe 3 or 4. Looks like y changes maybe by a factor of 3 or 4 when x doubles. Okay, so based on these 3 points, I see y appears to change by a factor of 3 or 4. Now I want to go ahead and come out here to the right someplace. Let's say right about here. Okay, and then I want to come in twice that far, which means I'm thinking about here. Let's see if this and this, maybe just a little further. Okay, and let's just do a couple more to try to get a little better handle on this. Well, this one's going to come way up. If we extend the graph a little bit, it looks to me as though the y value is going to end up here someplace. Okay, so we've got a y value here and a y value way up here. So let's see, one of these, 2, 3, 4, that looks like almost 5. Okay. Okay, so I would say that any number, 3, 4, or 5, would be a reasonable estimate of the factor by which y changes when x doubles. Now, in fact, the way I set these numbers up, and the way they should, in fact, come out for a flow experiment, it should be very close to Forkling. And we know that the Forkling graph, or we can figure out easily enough that the Forkling graph is the graph of y equals ax squared. Now, having a graph of y equals ax squared, and knowing many points that lie on or close to this graph, we could take a point on the graph and determine from the y and x values of that point the value that a should have. To get a good typical x and y value, our graph is not likely to pass exactly through any of the data points because of anomalies, uncertainties in our measurements. So we don't want to pick a data point. It could be away from the trend of these points. Now, the way I've drawn these points, it looks like the curve pretty much goes through most of them, but that won't always be the case, and we never want to use data points or points that we got directly from individual data points. We want to use the trend of our curve. The trend of this curve, let's just take this as a sample point, okay? And this is one of the points we used in determining whether the thing doubles or triples or fourples or whatever. But here's a point, and it looks like the x-coordinate is about 550, and the y-coordinate looks to be, if this is 50, about 57. Okay, so that's my best honest estimate of the coordinates of this point. So if we plug that in, we get our function. It's y equals a times x squared, where in this case x is 550 and y is 57. So that a is 57 divided by 550 squared. Now 57 over 550 is pretty close to 1/10, so this is going to be pretty close to the square of 1/10, which is going to be 0.01. But I think it's going to be 0.01 something, and let's see, I think that something's going to be off by about 4%. I'm thinking probably 0.11 or 0.12, but let me figure it out. Well, I nailed that one. Late and I'm getting hungry, only excuse. It's 0.00019. I squared the quantity 57 over 550, and that was kind of a bonehead thing to do. So our y equals ax squared Forkling model is y equals 0.0019x squared. And we can, of course, check this by plugging all these x values into this and seeing how the y values compare.